Welcome to the final PowerLearn presentation. Our goal is simple, to bridge the gap between learning and industry.
PowerLearn was designed with a very specific audience in mind, university students and educators in the field of business intelligence and data warehousing. Our primary target market consists of undergraduate and postgraduate students at institutions like the University of Wollongong who are motivated to develop practical, industry-ready skills before entering the workforce. What we found during our research was that many students graduate with strong theoretical understanding, but very little hands-on experience with real tools like SQL, SSIS, SSAS, and Power BI, which are essential in the data analytics industry. PowerLearn directly addresses the skill gap by providing an interactive, self-paced learning platform that allows students to experiment with real-world datasets and sandbox environments. This means they're not just learning concepts, they are applying them as they would in a real job. For students, this approach offers flexibility, accessibility, and engagement. They can learn at their own pace, receive adaptive feedback based on their quiz results, and continuously build confidence in applying technical skills. In essence, PowerLearn runs theoretical education into a practical, job-ready experience. Our secondary target market includes educators and academic institutions. Teachers need better visibility into student progress and outcomes, and PowerLearn supports that with a dedicated educator dashboard. It allows them to monitor student performance in real time, identify areas where learners are struggling, and tailor support accordingly. This not only improves teaching efficiency, but also enhances overall learning outcomes. Universities also benefit from adopting a tool like PowerLearn. It strengthens their reputation for producing industry-ready graduates and modernizes their course delivery without major infrastructure costs. Ultimately, we target these groups because they share a common challenge, the disconnect between the academic learning and practical industry application. PowerLearn bridges that gap, empowering students to become job-ready and helping educators deliver more impactful data-driven teaching.
Through market analysis, we identified a critical gap in existing education platforms. Many emphasize either vendor-specific training or overly generic content. This imbalance has created fragmentation in skill development, leaving graduates unprepared for the job market. Our competitors are defined by three key categories. Online learning platforms, such as Udemy, are highly saturated, featuring minimal simulation options and focus on accessibility and affordability. They promote self-paced learning, however they lack the required depth to ensure industry-ready skills are learned. Universities focus predominantly on theoretical learning, often neglecting sufficient practical development. As a result, graduates are lacking critical, hands-on experience that is required by industry employers. While universities provide access to experts in the field, it comes at a high cost with no flexibility on how or when you study. Vendor-specific training, such as Microsoft, offers a single solution model, focusing on a specific tool or product. While this training does provide hands-on experience, it lacks exposure to competing tools, fails to teach broader concepts, and does not emphasize foundational principles. PowerLearn bridges the gap in the market with distinct advantages over the current products and existing solutions available. PowerLearn has been created from the ground up to provide a fundamental understanding of how business intelligence and data warehousing works, while also providing exposure to underlying technologies and developing proficiency with hands-on tools, an experience that our competitors do not provide in a singular solution.
At its core, PowerLearn isn't just another e-learning platform. It's a complete solution to one of the biggest challenges in modern education, the gap between what students learn at university and what they actually need to succeed in the workforce. Where most systems stop at theory, PowerLearn takes the next step, giving students a place to learn, apply, and master real-world business intelligence tools in one seamless environment. Through our adaptive learning engine, every lesson dynamically adjusts to the learner's performance, ensuring that no student is left behind, and advanced learners can continue to be challenged. Our live sandbox environments are one of PowerLearn's biggest strengths. They allow students to safely experiment with professional BI tools such as SQL, SSIS, SSAS, and Power BI directly in the browser. This means students gain the same practical experience they would in a real analytics role, but without needing complex local installations or licenses. Educators also benefit through built-in analytics dashboards, providing data-driven insights into student performance and engagement. This turns teaching into a measurable process, one where progress can be tracked and outcomes can be improved using real data. PowerLearn's design is fully responsive and WCAG 2.2 compliant, meaning it's accessible on any device and inclusive for all learners. And because it's completely free to access, it removes financial barriers that often hold students back. Ultimately, PowerLearn bridges the gap between learning and industry. It transforms how students prepare for their future careers and how educators deliver practical, outcome-based education. It's not just an academic tool, it's a launchpad for the next generation of job-ready professionals.
To bring our strategy together, we've mapped the core elements of our approach using the marketing mix, the 7 Ps that define how we deliver value to the education industry. Product. We've created an engaging sandbox-based platform designed for both students and educators. It blends academic theory with real-world technical application, empowering learners to develop job-ready skills in business intelligence and data analytics. Price. PowerLearn is completely free to access, removing barriers for students and institutions. This supports educational equity and broad adoption, ensuring everyone has the opportunity to learn, practice, and grow. Place. Hosted securely on Fly.io using AWS Firecracker for scalability and reliability, PowerLearn is accessible anywhere in the world, whether on desktop or mobile, making learning flexible and inclusive. Promotion. Our core message is clear and consistent, bridging the gap between learning and industry. We promote this through digital posters, QR codes for instant access to the platform, and partnerships with universities and student outreach programs. People. With key university partnerships, educators provide continuous support and guidance to their students. Insightful analytics give teachers visibility into student progress, ensuring responsive and personalized learning experiences. Process. A structured learning path supported by knowledge checks and adaptive loops helps students master challenging concepts. Safe, interactive sandbox environments let them apply what they've learned using industry-relevant datasets. Physical evidence. PowerLearn's modern, intuitive interface speaks for itself. It's clean, minimal, and accessible. Every design element promotes optimism and focus, ensuring comfortable study sessions. Together, these 7 elements form a cohesive strategy, one that transforms learning from passive theory into active, real-world experience.
So now that we've covered the marketing and product aspects, let's dive into the technical side of PowerLearn. At its core, PowerLearn is a web-based adaptive learning system built for both students and educators. On the front end, we use React, creating a fast, responsive single-page application that feels like a native app on any device. On the back end, we chose Fast API, a high-performance Python framework that allows for modular, RESTful design and fast response times. Our database layer is supported by PostgreSQL, providing reliability and ACID compliance for persistent data. For identity and security, we use Auth0, which manages authentication and authorization securely with role-based access control. One of the most important components of our architecture is the sandbox environment, which runs on DuckDB. This allows students to safely experiment with real BI tools and data, completely isolated from the production systems. And finally, the platform is deployed on Fly.io. This leverages AWS Firecracker micro VMs for efficient scalability and Cloudflare R2 for storing static files and providing DDoS protection. From a development perspective, we followed a strict agile methodology, working in 2-week sprints to continuously deliver and refine key features. We manage our workflow using Jira for sprint tracking, GitHub Actions for continuous integration, and daily collaboration over Discord. This was supported by Confluence for documentation. Our main focus areas through development were designing and testing the adaptive learning algorithm, ensuring secure sandbox integration for BI tools, maintaining data protection compliance with the Privacy Act 1988 and OWASP Top 10, and meeting accessibility standards under WCAG 2.2. As a result, we successfully delivered all 15 out of 15 core requirements, with each major feature being fully tested and approved by our supervisors. Now let's talk about our architectural philosophy. PowerLearn is built on a modular monolithic architecture, meaning we maintain a single deployable unit, but it's organized into well-defined modular layers. This gives us the best of both worlds, the simplicity and performance of a monolith, combined with the structure and the scalability of a microservice-based design. Our architecture is broken into several layers: the client layer, the application layer, the data layer, and the infrastructure layer.
Looking at the core technologies used in the PowerLearn system, let's start with Fast API. Fast API is used for ASCII, async, IO-bound operations with automatic OpenAPI docs and pydantic validation. SQL Alchemy uses type-safe ORM, connection pooling, and Olympic migrations. Support without PostgreSQL instance. DuckDB is used for columnar storage of analytics, allowing dashboard queries using DuckDB significantly faster in processing power than PostgreSQL. Celery is used for background jobs of reports and bulk operations without impacting our transactional database, and UVcorn and Gatecorn are our ASCII server with multi-worker concurrencies, enabling multiple UVcorn workers to work in tandem with Manycorn. Front end, we use React 18, our component architecture with concurrent rendering. Our Redux toolkit uses predictable state management with reduced boilerplate to increase productivity, and our Material UI uses pre-built accessible components with a theming system. Auth0 is used for JWT authentication, MFA potential, token refresh, and protected routes. Axios is our HTTP client with automatic JWT injection. Moving on to infrastructure, we have PostgreSQL, which offers ACID compliance and constraints to enforce integrity at the database level. Redis 5 offers session storage, caching, and rate limiting counters for highly utilized routes and interfaces. And our Fly.io via AWS Firecracker offers our managed PostgreSQL instance, auto-scaling in our machines, health checks, and rollbacks. Cloudflare R2 is used for our large static file store, particularly and only for our VM images, and also offers DDoS protection and global CDN edge networks. Docker and GitHub Actions are used for our CI/CD pipeline, with Docker providing containerized packages that are immutable for our deployments, and GitHub Actions triggering a deployment every time we merge to a main branch. Looking at our core innovations, let's take a look at the adaptive learning engine. We have a concept hierarchy of courses, which make up levels, which make up concepts, which make up modules, which are typed to questions. We use a concept mastery table to track per student concept masteries, where we have questions attempted and questions correct, and a mastery score is an algorithm based on correct versus attempted questions, reaching a mastery threshold. The adaptive loop goes something like this. A submission of an answer triggers the evaluation of the correctness, which updates the mastery and then checks the threshold criteria. This threshold criteria then triggers a detour if the student is found to be struggling and returns the feedback. The innovation in this is where our database transaction process is happening. We use one singular database transaction process with any failure in the adaptive loop, causing an automated rollback to the previous operations. Our detour detection methodology uses our detour service with a check for struggle analysis. It utilizes the success rate over the last 5 attempts, and if a struggling count of below 40% is found, it triggers based on the mastery threshold failures. It also accounts for consecutive failures and then extracts failing tags from incorrect questions found. If a detour detection is found, it then triggers a detour session with the failing concept tags aligned to the failed questions of the user. This then assigns remedial content from the remedial pools, which are tag matched and prioritized, as well as aligned to difficulty levels. We then use an additional mastery threshold system on the remedial content to trigger an exit for the user. The remedial pools, which are used in these detour sessions, are seen as curated collections of modules with scaffolded lessons based on particular tags. These are used for easier practice questions with hint functionality built in, and video tutorials also supported. The selection algorithm for this remedial pool content uses tag matching sorted to the priority, then based on the difficulty appropriateness. We have interfaces that supports teachers to add, change, and create new remedial pools as well. We then have analytics integration with adaptive decisions able to utilize our DuckDB database when required for teaching insights on the dashboard. Looking at our next innovation, let's move on to our sandbox SQL, OLAP, and ETL tools. The challenge here was how do we let students execute arbitrary queries without exposing data, allowing resource exhaustion, or enabling malicious behavior. Let's look how we've done this. First, let's look at the SQL sandbox. This runs on SQLite. Upon a session creation, we have a copy template DB, which copies the template to the particular user's session ID. Security layers we use here is keyword validation, which blocks malicious queries. We then have a timeout clause, which has a 10-second maximum execution, and then result limiting, which reduces the number of rows that can be returned. We additionally have injection prevention using parameterized queries and input validation, and a session lifecycle that automatically cleans up on expiration after 24 hours. Next, we have our OLAP sandbox. Our OLAP sandbox utilizes our DuckDB environment. Again, here we leverage DuckDB for its in-process analytical process. Our database is particularly well suited as it provides analytical capabilities and window functions, OLAP cubes, and aggregations while maintaining the same security posture as our SQLite service. Students can practice complex analytical queries without requiring separate server infrastructure, using a similar process to the SQLite sandbox, where we have session-based images of databases for each user. We then move on to the ETL sandbox. The ETL sandbox enables extraction and importing of users' own datasets of CSV, JSON, and Excel files to a 50 megabyte limit, and then allows transformation processes with Python-like syntax, which loads into our DuckDB database. All the processing across all three of our isolated processes, our SQL environment, our OLAP environment, and our ETL-like dataset, happens in isolated processes with OS-level resource limits to ensure there was no data leakage into the production environment. This also enables us to use concurrent execution as in-process databases with no TCP overhead, and enable theoretical hundreds of concurrent sessions per machine with a significantly lower resource cost than provisioning databases on a per user requirement. I'll now move on to the demonstration. Now that we've gone through our design philosophies, let's show the actual implementation. First, let's start with main.py, the fast API application entry point, and the main core services for our backend. Here we can see our fast API app is added, and we have middleware added in layers. We have clear error handling, ensuring that if middleware is not available, we do not cause excessive failures on the front-end services. We additionally have our course configuration, which ensures we know if we're hosting it in our production environment or if we're doing development on it. We have our clear logging services, API routes, which we initialize in our api.py for imports and exporting of API functionalities. And we have our health services for our backend health checks. Moving on here, I will quickly show you our middleware. Our middleware captures every API call we handle and ensures that each request flows through this middleware pipeline with clear functionality and clear security in mind. Our middleware supports our logging middleware, which logs every single call the user makes, as well as our rate limiting middleware, which is used to ensure we do not have DDoS attacks and each user is fairly using the service. We also have our database session management, which again ensures we are correctly handling errors. And our adaptive learning environment is used to continuously calculate the current metrics of our adaptive learning models and ensure we are not causing any errors in the remediation processes or our restart services. Moving on from this, I will quickly go through what our adaptive learning code looks like. Our folder structure here uses the backend, which has our app, our version API, our core services, our models we use for databases, and our database schemas, as well as continuous logging, Docker files, and TOML files for configs. Now let's look at the adaptive courses. Our adaptive course has been redesigned from our initial scope to use a clear course structure of 100, 200, 300 levels for introductory, intermediate, and advanced. Our course levels are clearly structured and is where all our magic happens. This code processes student submissions and triggers detours. As we can see here, we have our adaptive course structure. Our adaptive course structure includes our level models, and our level models then contain concepts. Our concepts then contain concept modules, and our modules will then serve lessons. Lessons are hidden within our modules, and we then have a logically separate concept question model that we use to ensure we have clear tagging, and we can clearly track user question attempts, failures, and the concepts and lesson types we'd expect to see that user have seen. We then also handle enrollment, and as we come here, we see a core component of our remediation process, which is our concept mastery. What this does is ensures we have almost near real-time processing of the user educational journey. We have clear data to ensure we know the attempts a user is having when they've started, their current enrollments, the concepts they have seen, and what their mastery is. And what we mean by that is how many questions they've seen and how many questions they've got right. Based on that, our attempt structures will then also contain tagging. Our tagging is what we use to create our core detour sessions. Our core detour sessions captures our concept tags, our failing tags, the reason for the creation of the session, and also the status of the detour session. We use remedial pools, which are a new type of concept, where they're separate lessons from the core educational journey, but are highly adaptive and infinitely customizable. This is then tied to our detour service, which is part of our core portfolio of functionalities. What this does is manages the adaptive remediation content where students struggle with particular concepts. It will route them to personalized detours based on the tags. Here we can see our detour service manages our remediation pathways, and now also dynamically loads configurations from our production database. If we do not find dynamic configuration in the database, what we'll do is use existing questions that we find in the core pathways. However, when there are custom remediation pools, we will check the student for struggles, get the recent question attempts, calculate their ongoing mastery score, seeing if it matches with what our current success rate threshold is, find consecutive failures where there is consecutive issues, and identify the tags which we have seen the student failing at. We then return the failure tags along with the success rate and calculate what our concept mastery is. If it reaches below the threshold, we will then create a detour session, ensure that the student does not have an existing session, and create a new session with remedial pool content set to what our custom settings are on the backend. We then have a dynamic selection criteria where we look in the remedial pools, IDs related to the tag content, and serve those to the user as supplemental content type. Our sandbox services function fairly similar, so I'll run through them quite quickly. What we have is a clear service provider, but they are distinct and logically separated from the rest of our architecture. What this means is we have multiple security layers, particularly in our create session functions. Our create session functions ensure each student gets their own database file in an isolated directory with no shared states, ensuring using in-processing analytical data frameworks with query execution and query validation with parameterized queries. We have several security layers that are associated with this. Our first is our blocks. We use blocks to block dangerous operations, and subsequently we use session timeouts and execution timeouts to prevent runaway queries, in addition to using result limiting to prevent memory exhaustion attacks. Overall, ensuring that we have clear exception handling and error handling that does not leak into our existing production databases. I'll move on now to quickly show our OLAP functionality. We first define OLAP cubes. We use these as sample data sets for users to explore, which is connected to our OLAP engine. Our OLAP engine utilizes DuckDB to provide real production-grade OLAP functionalities. We use pre-aggregated cubes from our definitions to drill down, slice and dice, create proof of tables, measure with KPIs, and also create aggregate awareness. We can see here that we use our DuckDB with in-process analytical data handling through a core OLAP engine. This ensures that all functionality is defined with database operations, and the user does not access the core database, but instead uses the functionality with defined parameter blocks. Where this comes to life is through our OLAP sandbox service. Similar to how we saw the SQL service, we see a create session function, our query execution, and our cube creation, as well as our engine initialization. This is separate for all users, ensuring that we have logical separation across all databases, using SQLite for our SQL sandbox, DuckDB for our OLAP, and part of our ETL service. Our ETL service is again different, where we create file directories in the session. Session file directories create sample data, allow uploads, missing, exporting, and data handling of JSON, CSV data types, and also Excel data types. We then clean data and allow pipeline execution across the ETL service, again, SAM to a user-specific session. I'll now move on to what is our front end. Looking at our app code here, we see this is the core of how we use React. We use React with Redux for state management and Material UI for our components. Our Redux provider gives us global state management with a theme provider, ensuring we have consistent styling, and private route enforcement here, which ensures we enforce authentication with our Auth0 provider. Authentication is handled through a custom loop, a hook, which is our use API and our use auth loops. What this does ensures that our Auth0 client cannot be bypassed, and our API client, again, uses our private routes to ensure what type of access a user should have.
That concludes the PowerLearn presentation. Thank you for listening.